Hi, everyone. First of all, I would like to thank you, AMD, for hosting this event, and it's for the opportunity to be here. I will present about challenges in building an IVI system. This subject is pretty big, so I planned this as, I call it a 10,000-foot overview. So it's literally thoughts on pain points on the way to achieve the final goal of building efficient IVI system for the vehicle. First of all, let me introduce myself. So I'm a staff software engineer at Ford Motor Company. I joined last year. I don't have much automotive background. My background is mostly embedded system designs, and I had opportunity to work on embedded hypervisor for quite time in the past. Okay, so what is the IVI? IVI is in-vehicle infotainment. That's pretty much any digital system in the car cockpit, as some would say. And infotainment is information and entertainment. It's a combination of two words. So here is the nice cockpit schematic demonstration of what normal driver will see. There's some gauges, which shows some indicators. It literally sits behind everything which sits behind the steering wheel. It's called instrument cluster. The term is instrument cluster. There is also a central console, which nowadays shows some infotainment content, like music, navigation. Historically, all of these big components were managed by individual ECUs. ECU is electronic unit, which somehow connected to the network of the vehicle. The problem here to solve is now we want to optimize. We want to get rid of multiple dependencies on different hardware blocks, still provide good user experience and efficiency. Let's quickly walk what instrument cluster is. Instrument cluster, that's gauges, indicators, any status of the vehicle for the driver. The basic functions are this regulatory. It's a gear selector indicator, drive, rear, parking mode. That's absolutely speed indication, and that's indication of either fuel for ICE cars, internal combustion engines, or it's a battery status. And then it's also a bunch of indicators, which in industry it's called telltales. Literally, that's an indicator of malfunction of any block in the vehicle or status of operation, like passenger seat belt sign, or airbag malfunction, or parking brake enable, or oil pressure. There's like long list of those. It may also include climate control. And interesting that why I listed it here in instrument cluster is defrosting is regulatory stuff. May also include rendering of ego car. Ego car is another term, which means self car. You can imagine if a lot of cars you put it on the reverse mode, and while you start moving backwards, there will be a nice view of surrounding environment on the central console, which shows you where the curbs, where the lines, where the cars, maybe some other objects potentially on your way. And that's, of course, RVC, rear view camera. Infotainment cluster covers all the functions which makes the driver experience or passenger experience pleasing. So it's rich sound effects, audio effects, most of all navigation, hands-free calling, vehicle settings, and projection. Projection, that's another term which means the smooth pairing of your personal gadget with your vehicle to enable using your favorite apps for navigation, playing music, make your driving experience better. And software updates. That's also crucial nowadays. So now, giving that blocks, how Xen can be involved in building such system. So this is the same schematic representation of the functional blocks of the cockpit. I roughly map them to VMs to represent what can be one of the final designs. So instead of having multiple units, we might put one big, more powerful ECU, place Xen on top of it, and run all the functions in individual domains or virtual machines, which gives us, provides us hardware consolidation. We minimized number of units, which comes with minimizing or optimizing the cost of the vehicle, which is good. It also gives us more flexibility in software because we may mitigate some of the hardware fix at scale is very hard. Software scale fix at scale is cheaper to introduce. And also it can accommodate mixed criticality workloads, like instrument cluster should be maybe considered a critical workload because it needs to show information real time. So why Xen? There's a lot of pros and cons. That's my interpretation. I think this is a very mature and cool technology to work on. I like high standards for the code and specifically very picky reviews. Thank you for those. Obviously, safety is the priority. And in Xen project, it's pretty solid established roadmap for the bright future, how we can certify and use this in the vehicle. There's a nice public test infrastructure which can enable in-house testing, please bootstrap in-house testing of such products. Community for means a continuous support. It's very easy to reach out. There's metrics, there's mailing list, easy to reach out and get help, which is great. It's not the same as dealing with vendors, traditional vendors. And it gives the independence. So you choose your own destiny. You can go fix it, or if you don't have resources, you can hire somebody to fix it for you. And with independence, it also comes freedom of choice, what hardware you can use, which hardware platform, this big ECU I presented previously. So that has solid support for both most popular platforms, x86, ARM. With Intel, it's a bit simpler to choose. It's only pretty much two vendors, AMD or Intel. The drawback was originally designed for big servers, not for small embedded computers. In ARM world, it's a bit different. It's the opposite, many vendors, but sometimes you have to add some quirks in the for the BSP, for board support. But it's also designed for embedded systems. Then it comes to system boot. The IVI needs to boot in just a few seconds, and that's regulatory requirements. What comes with that? First of all, it's a parallel VM start. That's one of the topics Jason covered. It comes with a block storage virtualization. And if you need Android, there's also a lot of trade-offs how to boot Android. So yes, it works through OVMF, but is OVMF the right way? Maybe it should be booted from U-boot, or maybe the best would be just add in hypervisor support for Android boot protocol, which is absent right now. Anyway, there's a lot of open questions. It's a trade-off, even like with the hardware. Potentially, if there's multiple domains, that ideally would be having individual storage device per domain. That might be expensive. Probably it's possible to add a block device driver to the hypervisor and virtualize that in hypervisor. Looks like a lot of work.
Just to interrupt there are people that have put block drivers in the hypervisor. And there's a group done by some Xen server people that put an entire NVMe stack and TCP along with it in the hypervisor. So it does exist. It can be made to work. It's not pretty code.
Well, so one is the design choices anyway. The other design choice can be just a slim block storage device driver domain. So the next critical thing is a direct pass-through of hardware. In such complex system, some devices by design cannot be assigned directly to some of the domains. So SMMU or UMMU are absolutely required for such design. It's for performance and for strong isolation. And with direct pass-through, like in PCI, there might be some interesting problems with weird devices, third-party devices. The next big thing is the visualization. So depending on the design, multi-display or single display or heads-up display or maybe rear displays, there's a need to have a layering system with priorities for showing the content on the displays. GPU hardware is pretty expensive and it's complicated. So usually it comes to just GPU sharing. And GPU sharing is a complex, very complex task, which cannot go without performance hit or instability. This is hard to do. So here, turns out VirtIO GPU is one of the solutions. And there's a lot of work ongoing, both QEMU and Xen to support that. Same comes for the audio sharing. Audio sharing is critical, specifically because of the sound alerts. All sound alerts, those who have regulatory requirements, such as vehicle horn or signals for cross-traffic alerts, they have to be immediately voiced. So there's also audio hardware is complicated, so it comes to sharing the same hardware across domains. Some hardware allows to update the firmware for the audio devices. So some of those mixing issues could be mitigated by just updating the firmware. Most likely, it's complicated. It comes to talking to vendor, and takes a lot of time and effort. So usually the solution would be DOM0 merging all the audio streams from the mains and somehow maintaining the timing that there are no glitches on the speakers. Or again, potentially there's opportunity to have a dedicated audio device driver domain. Another challenge is the thermal thing. So this ECU is a part of the vehicle. It provides a hazard to the drivers. So there has to be some strategy to mitigate overheating. Very likely there will be high effort to prevent overheating in general. Like the ECU very likely will be linked to the centralized vehicle cooling system. So coolant will be driving through that box. But still, there's a chance to overheat. In this case, it's better to audit the vent and then try to put the system in a safe state, like turning off displays. So the driver at least can park the car safely. And it comes to potentially having a thermal policy governor, probably in Xen. The next big thing is STR, suspend to RAM. Suspend to RAM covers one of the regulatory use cases. It's a safety compliance, specifically with two things. It's RVC and vehicle horn. RVC there's strong regulations about showing the rear view camera once the driver puts the gearbox in the reverse position. Has to show within a certain amount of seconds, quickly. Same for the vehicle horn. When the driver enters the car, horn should be available almost instantly. So as you remember, this whole requirement for the IVI system boot was a few seconds. So a few seconds, that's too much to comply. So this is where suspend to RAM may help. Then the next thing is debugging and OS bring up, which is challenging as usual. Luckily, there are tools to help with that, like debugging through the serial console. There's PV console, but it may require modifications in the exotic OS, which may be problematic. And there's also UART emulator framework, which is available on ARM for free for DOM0, but for DOM0 on x86, it's not ready. The work is ongoing. Hope there will be progress soon. The next thing to mention would be message passing interface between the VMs. There is Argo hypercall with the infrastructure. Unfortunately, there is no full vSOX integration in Linux stack. That might be a good thing to address. And it also relies on out-of-tree kernel modules and libraries, which also not upstream. Event channels provide one-way signaling mechanism, and if any extra data needs to be passed, it needs complex buffer management, which is TV communication device, effectively. And lastly, I wanted to mention the VM configuration. It's a broad subject. I There's no standard tool stack which easily integrates with the board hardware description, which either system device tree or a CPI x86. Not easily integrates with build system of choice and the boot procedure. So my understanding, pretty much like all deployments, they have their own full stack and streams to get that. That's pretty much it. Thank you. Yeah, sure.
So as you mentioned, you face some challenge about the virtual GPU support during your integrations. And would you mind to share a bit more details about the GPU sharing, the challenges, or the graphics composition challenges you face for Xen at this moment?
What can you come again, please?
Yeah, there is one page you mentioned. There. Okay, can you go back to what the GPU? Yeah, sure. As you mentioned, probably you will face some challenge about the composition, about the graphics composition challenges. Would you mind to share some details? Because we are working for the GPU side support, and maybe I can get back and try to address the challenges. Yeah.
So I mentioned this subject as agenda because basically IVI is a building, it's a virtualization of multimedia. So it's a virtualization of graphics, it's virtualization of audio devices. It's challenging.
Okay. It's made, yeah, I know it's about medium. Is there a difference with audio? You know, the medium probably, if you if you use the AMD device, probably they are inside of GPU, and they will go with the graphics meta stack for doing the video playback. So what kind and do you know any you will say probably there is some challenge about overlay here. So may I know a bit more details?
I'm not sure I can mention a lot of details.
Okay, no problem. Thank you.
I also have a question on the GPU sharing. You mentioned on the right there, Virteo GPU support. Have you looked at or considered SRIOV for GPUs? That might make sharing a little bit less cumbersome or more performant.
Most of the time, SRIOV-enabled hardware is very expensive. And in this embedded systems, every penny counts. So that's hard to get such hardware. It would be nice. Same comes from, for example, for the block sharing, right? There is potentially block devices with.
There are GPUs with SRIOV support, but they're the high-end models, I guess, like the H100 and so forth. But I would imagine a car might have just one of these, right? So they cost quite a bit.
Yep.
Yeah, so the thing is, SRIOV is actually, it's the way that server hardware is going, but it's not only expensive as in money, it's expensive silicon area, it's expensive power, which is also why you tend not to get it in the smaller embedded systems.
Yes.
Yeah. So a car could have tens of ECUs, maybe more. How would you consolidate them all on one Xen, or you have multiple per zone, or? And the other thing is, would every ECU be?
So it's not the whole complete car.
Yeah.
So I'm evaluating only Xen for IVI, and that's pretty much the cockpit, what's inside the cabin. There's a lot more units outside the cabin, which controls engine, controls gearbox, controls like pretty much a network, like it's a robot. Right now, the car is a robot, where each component talks through the network, some sort of network.
Thank you. I would like to continue to clarify some SRV GPU problem just now. The reason of the GPU sharing for SRV, we will face some the performance overheads because once the SRV is working to emulate as the different multiple virtual function. But once we are doing the virtualization, we have to do the migration or word switch between the different VM. So the virtual function will migrate in their multiple VMs. So we have to they have to have a GPU scheduler to maintain this in the different VM, and we have to once the migration happens, we have to do the save and restore. The save and restore will cost a lot of time, and so once the VM is increased, the performance overheads will be super high. But the virtual GPU, they don't have this kind of problem because they in the hot side, it seems like they adjust a process for the host GPU. So they don't need to do any migration and the word switch. So that's the reason the virtual GPU here, the performance is better than the SRV GPU. Yeah.
I see. Thank you.
Thank you.
Yeah, there is one remote question. So, hi, can you ask your question, Marmarik?
Yeah. Hello, do you hear me? Hello? Does it work? Hello? Hello?
Oh,
We're
yes,
not
I
hearing
can
you,
hear you.
Marmarik.
I don't hear it.
Okay. Okay. Regarding the communication, you mentioned Argo.
Can you type the question? Sorry,
Oh,
we can't hear.
okay. Okay.
Okay, the question is regarding communication, Argo, etc. Have you looked at VChan?
VChan. No, I didn't look at VChan. Thank you.